Hello, and thank you for taking the time to watch this video. Today I'll be walking through the application of a random forest classifier against a breast cancer data set. So to get some housekeeping out of the way, you'll see the acknowledgments for the funding source for this particular data set, the investigators who gathered the information, and a reference to the data set, as well as the URI, where you can access this data if you're interested. The owners of the data request that this information be included anytime the data set is used, so it's captured here. The table here describes the various features that are included in the data. So there are 16 features. I do want to focus on just a couple of items here. If you're interested, you can dig more deeply into it, but some things that I'm going to be dealing with a little later on, and just to set up for that. If you'll notice, for most of these features, if a 9 is included as one of the classes, it basically means unknown. So 9 unknown, 9 unknown, 9 unknown, and I'll be dealing with that later. Also, if you notice down here, there are 2 features that relate to a cancer diagnosis. There's cancer and invasive. I'll be dropping the cancer feature later because it's a little more exclusive in that it's only capturing if the woman was diagnosed with invasive or ductal carcinoma within 1 year of the screening, whereas the invasive feature is actually a broader, a diagnosis of any type of invasive breast cancer within 1 year. So I'll be focusing on that as the target variable. There's a training feature here, and I'll be dropping that. The reason for that is this data was originally put together by a group of doctors who were experimenting with applying logistic regression to this data set back in 2006, 2007. And what they did was for the data points that were included in their training data, they had indicated in that column, but it's really irrelevant to what we're doing with the data here today. Also, there's a count feature here that I'll be dropping. The reason for that is the overall data set represents almost 2.4 million screenings. And many of those ended up being duplicates of one another. So to quote-unquote normalize the data, what the researchers did was, if, say, there were 5 identical response sets in the data, they eliminated 4 of those and added this row, or this feature, and then for the remaining data, they put 5 in there to indicate that there were actually 5 of that particular response. So I'll be dropping that later on. So importing all the tools and libraries that I'll need to do the analysis, reading in the data set itself, then just doing a quick look at the data, just to see what the categories are, doing a describe. Again, just taking a quick look. Then, as I had indicated earlier, I'm dropping those features that aren't really applicable to the analysis that we're doing. And then this is the data that we'll be actually starting to do our cleaning and prep with. 181,000 unique rows and 13 features. So the first thing is I use getDummies to split out the variables into the various classes. And I won't go through each one of these, but I will walk through one of these just to give you a feel for what's being done. So the Hispanic feature here, I use getDummies to split it out into the various classes. Then I drop the Hispanic feature itself because I captured that same data using getDummies in the separate classes. Then, as I had mentioned earlier, I drop the 9 because that's a responsive unknown, so basically no response. And then I looked at the data. This was a yes/no. So I dropped the 0 so that what was left was Hispanic 1, and 1 in that feature basically means yes, the woman is Hispanic. So it just made more sense. And that's what I tried to do in all these. I dropped the unknowns and then dropped another feature to try to make the data make sense. Like for yes/no answers, keep the 1 so that the feature column name made sense with yes, as in yes Hispanic. And also dropping a feature to make sure to avoid perfect collinearity with the variable. So then taking a quick look at the data after that exercise, checking for nulls, and the shape of the data that remains is almost 182,000 rows by 29 features. So then doing the train test split, and I used grid search CV in order to identify the optimal parameters. Using, as I had mentioned at the beginning, the random forest classifier. So fitting the data, then identifying the best estimator for the data. So next I took a look at the relative importance of the features. How important was that particular feature to the task of classifying the data into a positive or negative cancer diagnosis within the next year. And you can see that obviously a bar that extends far to the right indicates a higher importance for this task. Then we do some accuracy and precision and recall calculations just to kind of get a feel for how good a job this particular classifier does. And the AUC in this particular instance was almost 61%. And you can see the rock curve here indicating that. So then I wanted to try to raise that to a better number. So I started dropping the features that were very low impact, the ones that made the least contribution to the task, and this is where I dropped those. After dropping those features, we end up with 18 features remaining that we're then going to go through the exact same exercise. We do the train test split. We'll use grid search CV to try to identify the optimal parameters and get the best estimator, and then redo our calculations, see how we did. Accuracy and precision and recall are similar, maybe a little better. The AUC did go up quite a bit. We're up at almost 67% now from the 61% we were at earlier, and here's the curve capturing that information. When I first saw these numbers, I was a little disappointed, but then I went out on the web and browsed through the publication where the original researchers had done their work, and was actually pleasantly surprised to see that the numbers that I came out with were very similar to what they had achieved in their published work. So I think the real limitation here is the data itself. We're not dealing with the very precise and very diagnostically significant outputs of tests or medical procedures. Really, this is primarily the type of information that you would see on an intake questionnaire that you're filling out while sitting in the doctor's office, with really the only procedure information included was the breast density that was determined through the mammogram. And I think that's the limiting factor in achieving higher ROC scores and higher precision and accuracy. So perhaps for a future implementation, this data could be combined with perhaps further diagnostic tests or some other sets of information to try to get to a higher number. Well, thank you for your time, and have a nice day.